Today we get to do one of my favorite methods of all time. As far as I'm concerned, if you're going to solve a system of equations and you got a calculator that does matrix operations, this is the only method. If you're solving two single variable easy, sure, elimination is probably faster. But if you have to solve for anything with crummy numbers or a large number of variables, matrix equations is the ultimate method. That probably even needs to get noticed. And I will show you why shortly. Wait till you see our last problem. Now, you have seen this before, but well, if you were in Algebra 2, you saw it there. In pre-calc, we used it a teensy bit, but not a great deal. So we have to remember, how on earth did we do this in the first place? Where did this all come from? And so the key thing is, in order to solve with matrix equations, you first have to learn how to divide a matrix. But you're going, you can't divide a matrix. She said you can't divide a matrix. You're right. You can't divide a matrix. Instead of doing 8 divided by 8 to get something to equal 1, what's the other way we can get that to happen? Well, we can do it by multiplying by 8 times 1/8. That also gets 1. It's the same operation as division, but we're using multiplication. Do we know how to multiply matrices? Yes. But you have to remember, what is this called when you multiply a number times its reciprocal? The fancy name for that property is it's the multiplicative, isn't that a great word? Multiplicative inverse. You're multiplying by the inverse. So our thing is, we have to figure out how do you do an inverse matrix. That's the first step. Once you know how to do an inverse matrix, then you can proceed to use it to solve all kinds of things. So the question of the day is, what was the method for finding an inverse matrix? Okay, it has a two-step process, and everybody wants to forget the 2 steps, or the first part of the steps. It's always a fraction in front times a matrix. The question is, how do I get that fraction in front? There's a number that goes on the bottom of that fraction. And we find it, if you recall doing Cramer's rule and determinants, we find it by doing a little cross multiply action here in the original matrix. So we are actually going to take AD, A times D, top left corner to bottom right. We're going to, key thing, subtract and do B times C. That can't tell you how much and how crucial that is. You must subtract. I don't like that. Let's do exclamation points. Key that you subtract there. Okay, now some of you are going, and yeah, and then you did some switch around with the numbers, you interchanged the numbers, and yes, you did. When we interchanged the numbers, we switched positions, DNA switched positions. B and C stay in the same position, but they switch their positive and negative signs. And so that's your general formula for finding an inverse matrix. Now, let's see if we can actually work a problem with this. Or actually, in this case, I just want to find an inverse matrix. So now that you have the formula in front of you, I am going to give you matrix B, which contains the numbers 5, 3, -6, -9. And I want you to find its inverse matrix. Okay, and so we're going to, of course, write it with the inverse symbol because we've got to keep straight which one's which. The key thing is to remember you have to have the fraction out front, then times the matrix with the numbers switched around. So the fraction out front, we're doing the cross multiply starting in the top left corner. I'm going to get -45. Across the other way is going to be -18. The question is, do I add or subtract? And of course, the answer is I subtract. Mission critical. I subtract. Without fail, I subtract. So now I go, okay, well, that's really then going to be 1 over 45 plus 18, which is 63. So 1/63 goes in front. And now I have to switch the numbers. Which numbers switch position? Which ones switch sign? Well, the -9 and the 5 are going to switch positions. So now I'm going to have -9 and 5 switching positions. What am I going to do to the other two numbers? The other two numbers I'm leaving in their original position. The 6 and the 3 are staying put. But what am I do to them? I am switching their signs. So now I'm going to have a -3 and a +6. So in reality then, my final inverse matrix would be 1/63 times -9, 6, -3, 5. Now, let me prove to you that that really is the same thing as multiplying by the reciprocal or multiplying by the inverse. We're going to take matrix B times that inverse we just found. Okay, if it really is the inverse, what happened when you take 8 times 1/8? You get 1. And so in matrix land, we should get the equivalent of a 1. So we're going to take, and I'm actually going to switch this. Since they're both 2 by 2s, the order doesn't matter. I just want that fraction out front. So I'm actually going to write the inverse first. It is easier to do these with the inverse first. So I have the 1/63, the -9, 6, -3, 5. And I'm taking it times the original matrix, which was 5, -6, 3, -9. Okay, leave the 1/63 sitting until the last possible moment. And so if I do that, I am simply going to multiply, as always, rows times columns. And so here we go. First number times first number, I'm going to have -45. Second number times second number is a +18. Excuse me, did I cancel, copy that right? Because that's not going to come out right. Oh, wow. You should be screaming at Mrs. Marcus. She can't add. Whoa, dudes, over here, yipolas. Holy mackerel. That should have been -45 plus 18. Okay, so I'm a little brain dead. This is the 6th or 7th lesson I've taught today. And so I was actually -45 plus 18. So sorry, that's going to make us have, wow, huge difference. -27. Wow. Well, my proof of this was about to crash and burn like no other. So let's try it again here with a -1/27 in front. And we'll see if we can get this to work. Okay, that looks a little better now. So -45 plus 18, first row times first column. I'm now taking first row times second column. So I'm going across the first row, down the second column. First number times first number is 54. Second number times second number is -54. Well, that's an interesting one. So we have 54 plus -54. That's going to make 0. Okay, now I'm headed to the bottom row. Second row, first column. That didn't show up. So I would have, first numbers would be -15. Second numbers would be +15. That, once again, is going to make a 0. And last but not least then, if I take bottom row, second row times second column, these are not going to make 0. I'm going to get 18 plus -45. Have I seen that somewhere before? And so if we finish this out, I have negative 1/27. If I add that up, look, I have negative 27, 0, 0, and negative 27. And what will happen at long last, you need to multiply the fraction in there. So you're taking negative 1/27 times negative 27. What happens when you take anything times its reciprocal? You get 1. You get a 0, you get a 0, and you get a 1. And ta-da! You have got the equivalent in matrix land of a 1. In the land of matrices, having a 1 down the diagonal and zeros everywhere else is the same thing as multiplying by 1. Just for your joy and interest, that is called the identity matrix. If you were to take that matrix times any other 2 by 2 matrix, you'll get the same answer back that you started with. It's the same thing as multiplying by 1. You get the same thing back. Now, you aren't going, well, actually, I take that back. You do have a problem, I believe, where it's going to have you actually find the inverse and multiply them together to verify that it really did come out to be 1, or in our case, 1001. Now, the good news is we're only going to be doing these by hand with 2 by 2s. There is a method for finding the inverse of a 3 by 3, but it's considerably more complicated. And with today's technology, it just doesn't seem to have a lot of purpose to spend extra time on it. So now let's go actually solve some equations, now that we know how to find an inverse. If you recall, these problems actually work out really, really, really sweet. You have to start with a matrix equation. You must show me this starting equation. Let's hear that again. Must show this starting equation. Right here, right now. Okay, so if I'm going to have, when we start with a matrix equation, it's a matrix times a matrix equal a matrix. That's why it's called a matrix equation. It's an equation made up of matrices. In the first matrix, you're going to pull the coefficient off the x's and the y's. In the second matrix, you're going to fill in an x and a y. And in the third matrix, you're going to put the numbers it's equal to. Okay, now check it out. If you take the row times the column, that's going to be 2x plus negative 3y. And it's going to equal the number on top, which is 22. If you'll notice, that's the exact equation we had up here. 2x minus 3y equals 22. If I do the same thing with the second row times the column, I'm going to get 9x plus 4y equals negative 64. It's a recreation of that equation, only in matrix form. Okay, now, here's the math side of it. I need to solve for x and y. So how do I solve for x and y when I need to then move this matrix to the other side? I can't divide the matrix, not allowed. So, and if I can't divide it, what's the same thing as dividing a matrix? Absolutely yes. We multiply it by its inverse, the multiplicative inverse. So I am now going to take this matrix times its inverse. And of course, if I do it to one side of the equal sign, I do it to the other side of the equal sign. Okay, now I'm going to let you shortcut. We know that when we take a matrix times its inverse, we're going to get that identity matrix. It's going to happen, so you don't have to show all that work. So in other words, what we just got here, if you go across and down, you have 1x plus 0y. So in other words, you're going to solve for x, 0x plus 1y, you're going to solve for y. So you really, from this point on, you don't have to write the 1001. It's not essential. You may ditch the 1001 if you really feel the need. But I needed to show it to you to show what happens. Now, on the other side, we really do have to multiply the inverse matrix times the 22 negative 64. The question is, what order must we write it in to get this done? Which would be the correct order? Somebody out there, I hope, is remembering our chant from when we did this before. Inverse first. inverse first, inverse first. So you're going to put the inverse down, then you're going to times it by the 22 negative 64. So I'm going to make the inverse matrix here. I should just switch the numbers around. Switch the numbers from which matrix is the question. That's a big question. Well, I'm taking the original matrix and I'm switching them. Hopefully somebody's out there screaming, but no, 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 you're forgetting the fraction. And I certainly am forgetting the fraction. I also need the fraction in front. 1 over the determinant value of this matrix. So in this case, if numbers out front do the cross multiply, it would be 8 and negative 27, and then I'm going to be sure to subtract between them. Mission critical. The numbers, I am going to interchange the 4 and the 2, and the 9 and the 3 are going to stay in their position, but they are going to change sign. It is now a negative 9 and a positive 3. Now, why did I do that? That's the inverse. I now need to multiply it times the 22 and the negative 64. And this is where the actual math comes in. You're solving for xy here. That's going to be 8 plus 27, or 1/35. You're going to save that till the very end, always. And now we're about to do normal matrix multiplication. We're going to take our row times our column. And so if I do that, 4 times 22 is 88, plus 3 times negative 64 would be negative 192. And we'll work that out in a second. We also need to do the same thing. We need to take second row times our column. And so if I take 22 times negative 9, I'm going to get negative 198, always a plus. And then I'm going to take 2 times negative 64. Whoops, I think I have that written wrong. I copied this off of my notes. That's supposed to be a positive 64. So somewhere in the deep, dark past, yep, that's supposed to be a positive 64. Not my day. So make this entire problem positive 64s. And so we will actually then have a positive 128, but that means up above. Yes, I should have. I also should add a positive 192 up above. So sorry about that. Good thing we hadn't added together yet. Last but not least, add them together. 88 and 192 makes 280. Negative 198 plus 128 makes a negative 70. And last but not least, you're timesing it by 1/35, or in other words, divide them each by 35. And you're going to come down to a lovely 8 and negative 2. So the solution to this system of equations is the coordinate 8, negative 2. Please write your answer as a coordinate. Okay, just to make sure you got the hang of that, we're going to whip over here and do one more by hand before we kick to our calculators. Now, you could do this by matrix equations. I still will maintain that you're insane if you do so. Doing this with a matrix equation and fractions, it can be done, but why would you torture yourself? Yes, we're going to get rid of the fractions. So, what would I have to take the top equation by in order to make it cancel the 4 and the 2? Well, of course, I would take it times 4. And so that's going to leave me with 3x minus 2y, but don't forget to multiply over here by the 10, in which case that's going to give you 40. On the bottom equation, I got a 5, a 4, and a 2, so it looks like I really do have to multiply by 20 to get rid of all those fractions. 20 times 2/5 is going to give me 8x plus 5y. And then that's going to 2 will cancel into 20. That'll be 10 times 21, so that will be 210. Okay, once you have it in the proper form, then yes, let's do the matrix equation. So if I set up the original equation, so I can show that it was indeed a matrix equation to start with, and it's got to equal 40 and 210. How do I isolate x and y? Yes, I times by the inverse. It's the inverse that essentially makes these two pieces cancel out. And yes, you may drop the 1001. Okay, now here's the key part. Do I write the 4210 first, or do I write the inverse first? And yes, it's inverse first with a fraction. So the fraction goes 1 over. You're going to do your little cross multiplying action here. We're going to take the 3 times 5 and the 8 times negative 2. So we are going to end up with 15, excuse me, wrote in the wrong spot, 15 minus, multiply the other way, negative 16. So we're actually going to get 1 over 31 there. Then, let me get rid of that. Okay, now we're going to do our switcheroo on our numbers. The 5 and the 3 are switching positions. The 2 and the 8 are switching signs. And we're going to multiply it by the result matrix here of 40, 210. Last but not least then, that's going to leave me with 1/31 times, and I need to do some awesome matrix multiplication. So if I want to do some nifty matrix multiplication, I'm going to go across my row, down my column. 5 times 40 is 200. 2 times 210 is 420. Be sure you add in the middle there. Notice, that is addition. But when you do, whoops, sorry, that's addition. But when you do that is subtraction. So major critical, addition, subtraction, keep it straight. Okay, now I'm going back to take the bottom row times my column. So 40 times 8, 4 times 8 is going to make us have negative 32. So put a 0 on that, negative 320. 3 times 210 is 630. Well, this looks pretty nice, except, yuck, I got all those zeros and I have to divide by a 31. Well, we're going to hope I didn't mess it up again. If I add them together, there's 620. Well, that looks pretty good. If I add these two together, I have 310. And wow, look at that. They're both divisible by 31. 31 goes into 62 twice, keep the 0, goes into 310 10 times, and we have a solution with a coordinate of 2010. You gotta love matrix equations. They work so fast and efficient. Even while they eat some paper, they're really quite simple to do. All right, so for the big finale, the big finish, the woo out. Look at this baby. Yeah, mama. You're dying to do that puppy by hand, right? I have to admit, I have no idea how to do that by hand. I have no idea how to do a 5x5 inverse matrix. Well, actually, I think I do have an idea, but I'd have to go back and get some details. But it would be horrifically horrible without fail. So if we're going to do it by calculator, what would we need to do? And I'm not even going to write all this out because just setting this problem up was a nightmare. I would create a matrix, and in this case, I will let you shortcut, and you don't have to write the matrix equation. I would create a matrix that has all these lovely numbers in it. We'll do, and would have 5 rows of these. Okay, ugly, ugly thing. What I actually have to do, though, is I have to take, when we actually solve a problem, in reality, in the end, when we solve the problem, the real heart of the problem is right here. This is the solution to the problem. Oh, dude. Hey. I didn't know it did such a thing. Wow. Okay. How do I get it to go back? Escape. I'm trapped. I'm trapped in an enlarged problem. Go back together. Nope. Oh, there's an X up there. You're all screaming, CDX. Well, that was pretty nifty cool, huh? I got to play with this magic pen more. All right, so that part right there was the key part, the inverse times the result matrix. So all we're creating over here, this is the original matrix. How do I make it an inverse? The key thing of the day that we're going to have to do is that we have to be sure and put the inverse symbol on it before we then times it by the results matrix, which is the 401.2 down to the negative 4,621.5. I worked hard to make a really crummy problem. So, needless to say, you're not doing that by hand, so you're going to go to your calculator where I have already entered the majority of the numbers. You're going to just create a matrix. What one thing is missing, though, that I intentionally left out here, and hopefully you're noticing, well, she's got all the numbers, but it's just a matrix times a matrix. I'm missing the inverse. How do you put the inverse on it? You're going to hit the caret key, and then so that puts an exponent up there, and you're going to type a -1 in to put the inverse on it. Now it's going to take this matrix times the inverse, and we are, oh shoot, did I copy the wrong one down? I just tested it a little bit ago, and this whole thing worked absolutely perfectly. Oh, I did. I copied the wrong problem. Okay, well, we'll fix it here. Darn it. Okay, I had discovered I had missed down here in the bottom left corner a -6. So let's try it again. Woohoo! There's some better answers. Still not pretty, but certainly better. And let's face it, doing it by calculator was infinitely easier than doing it by hand. This is also a method, if you're going to solve for multiple variables, this is the only method. I mean, you can do 2 by hand. 3 is tolerable by hand. Anything more than 3 variables, this is your only choice. This is the way to go. I have had engineers come home and tell me they use matrix equations to solve for multiple variables. There's actually some examples of some electrical circuits and things in the problems in your book where they're actually using it to solve systems of equations. So huge thing. The only method to use. So matrix equations. It's the only viable method for 4 or more variables. Okay. You could do it with an augmented matrix. It'll work. That's another option you now have. You could do an augmented matrix, but let's face it, an augmented matrix with that's a lot of 1s and 0s before you get that triangle formed. So I still would contend matrix equation is the only real method when you have lots of variables. So you should enjoy this one. It should be old hat to you, I hope. And we will wrap up our last new material next time with the study of partial fractions.